Okay. Hi, everyone. Welcome to this week's 1W-MINDS seminar. Today, we are pleased to have Professor Laura Balzano from the University of Michigan. Professor Balzano is an associate professor in the Electrical Engineering and Computer Science Department at UMich. She also completed her PhD at the University of Wisconsin in Madison, where she was advised by Rob Nowak and Ben Racht. Her talk today is titled Efficient Low-Dimensional Compression for Deep Overparameterized Learning and Fine-Tuning. Just for participants' info, the talk is being recorded. You may ask questions during the middle if you want, but just be aware that it's being recorded. After the talk concludes, there will be time for questions, which will be unrecorded. Yeah, so I guess without further ado, Professor Balzano, you can take it away.
Great. Thank you so much, Santosh. And thank you everyone in 1W-MINDS for the invitation. I enjoy the seminar series in general, so it's great to be a part of it. Today I'm going to talk about efficient low-dimensional compression in deep networks. There's been a lot of work over the last 4 or 5 years showing that deep networks, both linear and nonlinear, have an implicit bias toward simple or low-rank solutions. And this work, we're trying to leverage that observation in order to actually improve training and fine-tuning and inference, improve in terms of efficiency, computational and memory efficiency. Okay, so as we all know, modern deep learning applications are making huge waves, not just within our community anymore, but also in the public with amazing performance for programming assistance, interaction through chat, image generation, image recognition, and so on. But unfortunately, all of these applications I just showed you are owned, trained, designed by massive, wealthy companies. So this figure that I like to show is from the ConvNext paper. It's from a couple of years ago. It made a really big splash, a very interesting architecture for vision tasks. And you can see here in this plot, they're showing their accuracy on ImageNet 1K, and they compared their model to other state-of-the-art models, ResNet, SWIN, Vision, Transformer. And they both trained on 1K and tested, and they also did pre-training on ImageNet 22K and then tested on ImageNet 1K. And you can see like these big bubbles that you see, that alone, just one of them was 256 gigaflops of training. But across all of the experiments in that paper, if my understanding of the table where they compare all of the required flops for training is correct, they used 2.5 teraflops just for that one paper to present their architecture. So, of course, it was the authors are from Facebook AI Research, so they have those kind of resources, but we really would love it if these kind of tools could be accessible more broadly. To put a finer point on it, it was estimated that GPT-3 cost $5 million to train, and GPT-4 may have cost $50 to $100 million to train. Okay, so not only do we not have those resources outside of those corporations, certainly if we did, we wouldn't be using them to train one deep model, okay? At least not at the University of Michigan. And, it's maybe questionable that those companies are also using that money just to train a model, but they're obviously getting economic value. That's what drives their their interest. Okay, but the goal, I think, for many of us is then how can we take the success of these huge machine learning models and make it accessible to many other applications and other people in other places, in education and environmental science and just general scientific pursuits, or government policy, other kinds of important applications in the world that we believe machine learning can potentially make an impact on. So the great paradigm that has been emerging recently based on these, amazingly successful models is one where we divide the training that is done at these corporations as a kind of first step, and then pass the architecture and the weights on to other applications to fine tune and then perform inference. So, the idea being that maybe in these corporations, say in the language modeling, they can pre-train, which is just training, but on this tremendous, huge raw data set that they have access to, and then give access to other institutions, to those weights, where using smaller amounts of data in more limited or specific settings, we can fine tune them and use for inference in our specific applications. And this is, helpful because hopefully the fine tuning and inference uses significantly less resources. Okay, so one example that's really cool is the University of Michigan has access to some portion, something with about GPT-3, and we can fine tune those models for specific educational purposes within the university. They call it MAZY. So different people are working on trying to get, query system for your class to answer questions and things like that. So, it's really happening in the real world right now. And so the goal of what I'm going to talk about is that we want to make this second two boxes, the fine tuning and inference, as efficient as possible, and that hopefully that will, make the success of machine learning widespread, give widespread availability. Okay, so the key takeaway that I'm going to share in the talk today is that when training a deep network, the dynamics of gradient descent typically occur in a low-dimensional subspace. And even in many settings, one that's invariant over the entire course of training. So we want to leverage that to compress the network during training, adaptation, and inference. Okay, and this plot, which I'm going to show again later, shows several adapted layers in a fine-tuned model. And this is the difference between the new layer and the fixed pre-trained one. And you can see in all cases that each layer, the final learned adaptation is low rank. Okay. And like Santosh said, please stop me at any point if you have any questions. All right, so to get into the work I'm going to share today, I'm just going to start with some observations from both nonlinear networks and then the last one, a linear network. I'm going to talk about deep linear networks, kind of try to motivate why they're interesting, not just because they're a little easier to analyze mathematically, but they seem to have useful properties as well. And then I'll talk about the theory that we've developed on invariant low-dimensional subspaces in the gradient dynamics for deep linear networks. Then I'll talk about applications in network compression and network adaptation, and that'll be the end of it. All right, so let's get into the observations, starting with notation. I have my standard machine learning notation of training data pairs data X label Y in dx and dy dimensional space respectively. And we're going to learn a prediction function f of theta that takes in the data X and hopefully predicts something close to the label Y. And that function is going to have a deep network form, either like multi-layer perceptron with the nonlinear functions or a deep linear network in the linear case. And we'll train it with some loss function. Cross entropy MSE are the two that we typically use in this presentation. Okay. Okay, so let's talk about a few observations we see from experiments that we run. So in this first observation, what I'm showing is the singular values of a delta weight matrix. And what I mean by that is if you take the initial weight matrix at time 0 and you subtract it from the matrix at time t, then that delta is what I'm looking at in these plots, okay? And you can see across all 4 of these different architectures that most of the singular values across iterations are very small, okay? And some of them, it's like very clearly only a low rank change between W at initialization and the weight matrix at time t. This in particular is for the second to last layer, WL minus 1. But it's across all, many different kinds of architecture. So this is the deep linear model, a multi-layer perceptron, both of those trained on MNIST with MSE and CE loss respectively. And then VGG and Vision Transformer, both cross entropy loss on CFAR10. So, linear, nonlinear, different types of nonlinear networks, we see this phenomenon. Here's another example, not just with training and the difference over time during training, but this is specifically in fine tuning. So in this plot, we're showing results about one of the weight matrices from fine tuning BERT, the language model, on the STSB data set, which is semantic textual similarity. And so there's several layers in the network, and we give the STSB to fine-tune BERT, and each layer gets, a new adaptation, right? It's the new weight matrix versus the old one, the original pre-trained one. And you can see here, so this is what we mean by adapted layer. This is the shallowest layer, the first layer, all the way up to the deepest layer of the network. And the difference between the original BERT weight matrix and the fine-tuned matrix, these are the singular values. So again, they're extremely low rank. And here we show how quickly the subspace converges to the final subspace of that adapted layer. So you can see for different layers, especially the shallower ones, it converges very quickly, but in general, it converges quickly to this, new low rank adapted layer. And
I'm
even
sorry to interrupt with a very naive question. The SV index, is that a log scale, or is that an actual number of singular values that are active? I mean, it doesn't seem like 8 or 7 is a reasonable number of singular values.
That's an actual number. And actually, I'll show you a little bit later. So this
4,
is
5, 6 singular values are having significant shift.
Yeah, that's right. And this is a specific, specific context. So in this case, like I said, just fine-tuning BERT, but I'm fine-tuning BERT with a low rank adaptation. So so I'll show you later, and hopefully that will convince you more why it totally makes sense. But anyway, yes, that's the number of
not a log scale. Okay, thanks.
Yeah, I can ask specifically about the scale actually, because that's not on this, right? So I can ask my student, but when you look at the numerical rank with a pretty low threshold, this is like the numbers of changing singular values between the two. All right, so even after these singular subspaces seem to converge, like say around 1500 iterations here, we can see the training loss is still decreasing, okay? So there's some training still happening, but the subspace is staying the same, all right? And that's one of the ideas here we want to focus on. All right, so both of those are, nonlinear networks. So here's a simulation study from a deep linear network where we have no nonlinearities, right? All of those sigmas that I had in my notation slide, are just the identity. And what we did here is we initialized this. It's a 3 deep linear network. We initialized all the weight matrices randomly and orthogonally. And then we trained it on low rank data. Okay, the data is exactly rank 3. And here on the left, I show the singular values of the first layer weight matrix, okay? But later I'll show you that it looks the same for all 3 layers. So like I said, we start with random orthogonal weights. So of course, at first, the singular values are all 1, okay? And then as training proceeds, we see that the top 3 singular values change and the bottom 3 singular values change, okay? So there's, you know, some change happening where it's being attracted to some low rank subspace, ideally this one, this data subspace. And, you know, it's basically using the lower singular vectors and values to also sort of adapt to that subspace, okay? So that's just the singular values, but, you know, of course, we could sort of randomly have singular values at every iteration and it could still look like this, but we also say the singular vectors have the same behavior. So this is the angle of the vector at time t with its initialization, and the angle in the first 3-dimensional subspace and the bottom 3-dimensional subspace increases. So it goes away from its initialization, whereas all the rest of them are flat in both the right and left singular vectors. Okay, so oh, I see some things in the chat, Santosh. Should I look in there, or is it okay if you do? And
I think Keith got answered Frederick's question.
Okay, great. So if you don't mind interrupting me if you think I should answer.
Yeah, of course. I'd probably do it like in the end of a slide or something, but
perfect, no worries. All right, so here, those are like empirical observations. Okay, so we, you know, decided, especially in this linear case, this exactly low rank case with a linear network, let's see what we can say theoretically. And many people have studied this problem and tried to say something about the low rank bias that occurs in gradient descent in deep linear networks. But we wanted to say something specifically about this fact that all these sort of, you know, middle singular values are staying the same. And it seems like that subspace isn't being used during training. If we, you know, could say something theoretically about that, which I'll say in the next section, then hopefully that structure that emerges can help us to more efficiently train deep networks, because we can focus in this low rank subspace, compress the network, and adapt networks with low rank adaptation layers, okay? And these figures I'll talk about later when we actually get to those parts of the talk, okay? All right, so like I said, you know, that last experiment I showed and our theory will be about deep linear networks. So I'm going to spend just a few slides to try to motivate why it's interesting, to, you know, besides just being easier to analyze. All right, so first, what I'll show a few slides about is we see empirically actually that replacing deep layers in a nonlinear network with linear layers actually does not often compromise accuracy. And it gives lots of the same behaviors as nonlinear networks. And so, you know, maybe understanding deep linear networks can be helpful in order to improve nonlinear networks. But then, you know, as many works have investigated over the last 5 years, it is easier to analyze the linear case, and we all hope and see ways to make it a stepping stone to more sophisticated analyses that include for nonlinear networks. So let me give you a few pieces of evidence for the first bullet. Now, go back to my notation slide for these deep linear networks. Just to be really precise, this is what I mean, right? All those sigma functions are gone, and I'm just multiplying WL through W1. We can also denote that as WL:1. That's the product of all those matrices, which of course itself a matrix. And then for all of this section, I'm going to train with MSE loss. Okay, so I'm training these W matrices, WX minus Y. Okay, so I said replacing deep nonlinear layers doesn't seem to affect accuracy. So let's look at one example. So here I've trained a 7-layer nonlinear multi-layer perceptron. And you can see the accuracy of prediction improves across layers. That's the blue curve. And then also the rank of the matrices as you get deeper into the network is decreasing, showing that it's kind of focusing in on some lower dimensional aspect in the data. Okay, so if we actually replace the whole deepest part of this network with a linear network, okay, so I'm going to replace layers 3 through 7 with a linear network, we get very similar performance, and you see this in, many examples. So this plot shows the same with training accuracy and rank, and you have the same behavior where the accuracy goes up nicely, and it looks sort of flattish, but it's kind of going up very slightly in those last several layers, and the rank is decreasing. So the linear layers are similarly increasing that accuracy and feature compression.
So do you also observe the same trend with the test accuracy?
Yeah, I have, I don't have plots on that right here. Sorry about that, but did you say is test accuracy also going up, or?
Yeah.
Yeah, and it's not 100%, but it's, similarly increasing. Sorry, that would be a better plot to include probably. Okay.
While we're asking questions, how big are these matrices? Just to see that 700 is like actually low rank.
Yeah. That's a really good question. I had a note on this, but it's in like the hidden part of my slides right now.
Yeah, I'm guessing like in the 10,000s at least.
I don't think it's quite that big. So I don't think this is like extremely low rank. I think it is decreasing, right? So I think it's more like it's the size of CFAR 10. What is that again? Is it like 2?
Oh yeah, I guess it's 32 by
or
yeah,
like
maybe
by 32.
But at least 32 by 32 by 3. Okay, maybe 256 by 256 by 3. Okay, that's pretty big then.
Okay. And the layers aren't necessarily, well, no, I think in this one they're all square until the last one. So yeah, okay.
Okay, and just so the horizontal axis, the shallow layers are nonlinear, and then the deeper layers are linear. Is that how I should understand? Okay, thanks.
Yeah, that's right. Great. Thank you for interrupting and all the good questions.
Well, thanks for answering.
All right, so here's another plot where we look at some metrics. I'm not going to define right now. If you're interested, we can go back later, of discrimination and compression of features. So this is related to the concept of neural collapse for those of you who are familiar with that. So the metric for discrimination, the higher means it's more discriminative, and you can see like as you get deeper into a network, it's more discriminative between classes. And for compression, the metric is smaller the more compressed the features are within a single class. And you can see in both cases, again, as you get deeper into the layers, it's being more compressed. And, of course, the key thing from this plot for me to say is I've replaced the deeper layers with linear layers and I get the same behavior. Okay, so, very natural question that we all had several years ago, and maybe don't have like an entirely complete perfect answer to yet, but we're starting to understand better, is why do we need depth in linear networks? Just like I said in my notation, right? Like WL times WL minus 1 all the way to W1, it's just a matrix. We could call it WL colon 1, we could just train that. So why can't we just learn these parameters and apply them to X? And this is, all the research that I've sort of cited already is looking into this and trying to understand this. But the key point that all that research makes is that the depth gives implicit bias towards simple or low rank solutions. And that depth and that bias improves generalization. Okay, so here I'm showing the same type of network I showed on the previous slides, either multi-layer perceptron or hybrid, where the first 3 layers are nonlinear, the rest are linear. And I just increased the depth from 3 for fully nonlinear, then to 15, okay? And we can see, like, for the hybrid network, we roughly always see improved test accuracy as we get deeper. This is only over 5 runs of random initialization, so it's a little bit noisy, but we see improved generalization. And also with the nonlinear network, for at least a time, there's improved generalization with depth. Okay, so that's the key to using deep linear networks and learning the parameters of deep linear networks as opposed to just learning the parameters of WL colon 1 alone. All right, so that's my motivation about deep linear networks. So now let's talk about—
Someone asked in the chat, what about depth 1?
Say it again, what about depth 1?
Yeah, that was the comment.
So like, I assume they mean like if I had somehow extended this down to be—
I would guess so. Jun Kung, if you want to clarify more in the chat, that's fine. But yeah, you can go ahead and answer that.
So it's sort of similarly bad as these 3. 2 is a little worse and 1 is worse. So
I'm sorry, Professor, I have a question. So why the test accuracy for fashion MNIST is low? I mean,
so with all the results that I'm showing, keep in mind that I'm showing them with these simple models, right? Like the deep multi-layer perceptron is just ReLU with fully connected layers, right? Or the deep linear network is just a bunch of fully connected layers. So the state of the art on fashion MNIST does not use an MLP, right? It uses vision transformer, or it uses CNNs and so on. Okay, so I'm not saying that these are achieving state of the art. I'm just using it to compare the full MLP and like some hybrid.
The hybrid. Okay. Yeah, thank you.
Yeah, great question.
And we do have a couple more questions in the chat if you want to read them.
Okay. So Ali asked about the in-class and between-class like compression and discrimination I mentioned before. That is a kind of a detour, but I'm happy maybe to come back to it at the very end. I have the definitions in my extra slides. And then Mole asked, Zainas asked if depth is held constant, does substituting the deep nonlinear layers with deep linear layers lead to any degradation in test error? So this is test error. In this case, I'm not sure if you wrote this before or after, but you can see that there's, in this region, the test error on MLP is higher than on hybrid. But actually, the deeper it goes, the better it gets for the hybrid network. And Molay, could you please comment on how low rankedness is related to better generalization? So it's just one form of regularization, right? So in general, we believe in optimization that simplicity bias is going to allow improved generalization because it doesn't overfit, right? And you know, the bias variance trade-off and overfitting in statistical learning is something we've understood for a very long time, as long as you know the model class that you should regularize for. In deep learning, somehow we're getting implicit bias and good generalization despite having, you know, for example, way more parameters that we train than we have data points that we use to learn them, which was very counterintuitive until I'd say the last 10 years. So I hope that helps answer those questions. Keep them coming. All right, so but let me get to some results. Okay, so we're going to focus our theory on deep linear networks. So again, I have this f of theta, which is just WL:1, right? The product of L matrices. And I'm going to train it using mean squared error loss. For the gradient descent on this loss function, first I'm going to start with an orthogonal initialization, epsilon scaled, okay, so that we can have a small initialization, but it's still orthogonal in this sense that depending on the size of W, if it's tall or wide or square, I guess, then both of these would be true. But this is what we mean by orthogonal in that setting. And then we're going to just use gradient descent, a kind of vanilla form, except with some of the typical parameters used in deep learning. So we have, of course, the learning rate, the step size, eta, and then we have the parameter lambda, which is what controls weight decay. Okay, so that's our optimization setup. Now, the assumptions I'm going to make on the architecture and the data in order to say something theoretically are the following. First, we're going to have square matrices, except potentially the last layer. Okay, so all the matrices are fully connected and have the same input and output dimension. A strong assumption is that the input data is whitened. So the matrix XX transpose is identity. And you know, you can do that with pre-processing, which requires SVD and inverse of your data set, significant computation, though it only happens one time, I guess. But still, that's a pretty strong assumption. And then we're going to assume that the target Y has low dimensional structure. And that can either mean it's low rank itself, or it could be a wide matrix. So, you know, one dimension is much smaller than the other. Okay, so the two cases that our theory considers is that the first that I'm saying, like low rank matrix, you could think of it in a low rank matrix recovery problem, like matrix factorization, sensing, or matrix completion. And then the case where I talk about Y being a wide matrix, we consider it in, for example, the multi-class classification case, where the output label for each data point is a one-hot vector. And so this wide matrix is only has only k rows and n times k columns. Okay. All right, so earlier, the plot that I showed, I just want to sort of remind you. So this was what inspired John to try to look into the theory of this invariant subspace. So it was a 3-layer network, a deep linear network. Dx, dy, and the middle layers all size 30. And the rank of the target Y was 3, okay? And I showed earlier the singular values vectors for layer 1, but you can see it's, you know, very similar in all 3 layers of this trained network. All right. So what can we say about this? So here's a theorem in a preprint we have online. We're training an L-layer deep linear network. All the matrices are square, including the target Y. So they're all the same dimension. Our data are whitened, and then YX transpose has low rank. It's rank R, okay? Define this M, I'm going to use it to be the difference between the dimension of all these matrices and 2 times R, okay? Which is like what we saw, the top rank R and the low rank R subspaces were the ones that were changing. Okay, so in this setting, the iterates of gradient descent for all those L weight matrices and overall time satisfy this decomposition. So each one of those WL can be decomposed as follows. There's a UL and a VL that are orthogonal matrices on either side. Critically, UL for one layer is equal to VL plus 1 at the next layer. So actually when they're multiplied, right, then that's identity. And in the middle here, we have a 2R by 2R block that's, you can think of as arbitrary. And then the bottom M by M block is a diagonal matrix with all the same values, rho of T. Rho of T is changing with iterations, but it's explicitly defined. And this W tilde, like I said, you can think of it as an arbitrary matrix, but at initialization, it's epsilon times identity, where epsilon, and so is rho at initialization. Epsilon is the scale that we used for initialization, which, yeah, I just wrote orthogonal initialization there, but if you remember from my previous slide, that's the initialization scale. Okay, so we have this decomposition where these U and V are not changing with time, with iteration, but the W tildes and rows are. Key is that these U and V are not, so actually all of the change in that W tilde is happening in this 2R by, 2R dimensional subspace. Okay, and that's the key for what we'll show later, compressing the training in these networks. Okay, so let's try to get a little bit of, sort of take something out of this, okay? So I had that, decomposition. We can say, okay, let that W tilde, just let's get its singular value decomposition like this. Then what I'm saying is the WL has this decomposition, this singular value decomposition, right? And this may not be ordered, but it's an SVD. And so the UL1 and the VL1 are being rotated by, whatever's happening in the gradient updates. But UL2 and VL2, this orthogonal space is not changing through the entire process, okay? And so the learning is only happening in this small invariant subspace. Okay, not only that, but when we look at the end-to-end weight matrix, as I said, the U's and V's match up, so they cancel in the product. And we have this W tilde L colon 1 in the middle, okay? So in fact, we can write the end-to-end matrix in this much simpler form, which has the U and V invariant, let's say, training subspace, with the training happening in these W tilde smaller matrices. And then these other, and they're orthogonal to the training subspace, having, just this rho factor, okay? And in fact, we started rho by initializing at epsilon, And this gives us a little sense of actually what happens as you increase L, right? So when you have something small and take it to higher and higher powers, it becomes closer and closer to 0. And we get a good approximation saying just this subspace and the training happening in this subspace is basically a good approximation for the training in all the layers of the weight matrices. Okay, so this is really what we want to leverage. And so, what I'm claiming and will show some evidence for is that with small initialization, we can run gradient descent on these W tilde small weights and get something as good as what we did in the original space. All right, so that was for the low rank Y case. We also have the case where Y is wide. So now everything is square except the last matrix. It outputs something to a low dimensional, R dimensional Y matrix. So you could think of this R as like the number of classes, for example. Then the same decomposition holds, and we know the formula for rho and everything, but now M is D, the X dimension minus 2, the Y dimension, or 2R in this case. All right, so, I have some pretty specific assumptions, and for example, the Whiten data being a pretty strong one. So I just wanted to show you what happens when we don't satisfy those assumptions. In this synthetic example, we don't whiten before we run, and we still get a similar behavior, though it's interestingly sort of less balance between the signal subspace and the opposing one. Oops, sorry. And then also we tried to use, different gradient method. Here we just use momentum, and we see the same behavior, though, in a different way. These are still the deep linear networks. So, all right, so how can we use this? How can we apply this? I'll try to go through this in just 5-ish minutes, so there's time for questions. Like I said, we can, try to run gradient descent only on these compressed weights. So let's try to see that in action on low rank matrix completion and low rank parameter efficient fine tuning applications. All right, so first I just want to mention, right, that we talk about inserting these deeper layers or having deep linear layers. Also, people talk about having wider layers is helpful for deep networks. So it has been shown, that deep depth and width give us benefits in deep learning. But of course, the drawback is the dramatically increased number of parameters and optimization time. So that's what we're trying to tackle. Okay, so here we think we can get the best of both worlds with this efficient optimization. So just sort of start with deep matrix factorization as the starting point. Sorry, I meant to remove this here. I haven't introduced that omega notation yet, but that's for matrix completion coming up. Let's optimize and only use these W tilde weights. Now, we can do some kind of overestimating of the rank that, of course, increases the computation requirement, but would hopefully, not have any overfitting issues. Okay. And we see that we can exactly get the same gradient descent dynamics. And this is still on the exactly low rank target matrix, but in significantly less time, okay? And we've used only LR squared parameters in our network as opposed to the LD squared of the original network. Now, when we move to the matrix completion problem, we insert this omega, which is a mask, a binary mask that tells us which entries of phi are observed, okay? So if you apply our method directly to this objective, the compression doesn't work because phi times omega, the Hadamard, the masked phi is not a low rank matrix. It doesn't satisfy the assumptions of our theorem. And so that's what you see here in yellow. The gradient dynamics are not the same, and the recovery error is poor iteration and time. Okay. So the way that we remedy this is, this was our decomposition that we're claiming is like the much simpler one that we can work in. And we're going to say we'll still use that decomposition, but not ask U and V to be completely invariant. So we'll update those as well throughout time. And we use a different learning rate for those variables, and they actually converge quickly, and we have an invariant subspace at the end of training. And that's what you see in this like cyan curve. So we get convergence in the same number of iterations and much more quickly because of the many fewer parameters. So original network complexity is LD cubed, and ours is LR hat cubed times or plus DR squared for the 2 U and V matrices. All right, I'm gonna kind of skip this so I can talk about low rank adaptation, though I want to mention briefly that we also do this within nonlinear networks by like taking one weight matrix and overparameterizing. So like this starts as just one weight matrix and we expand it to a product of 3. We get improved test accuracy when that happens, but of course, if you don't compress them, then the required computation time and memory and everything has increased. So we compress them, meaning the middle one is R by R, the outer 2 are D by R. Then we can get that test accuracy while like reducing the time and memory and computation back down again. All right, so now let me talk on a few slides about low rank adaptation. This goes back to a question asked a while back. So low rank adaptation is a parameter efficient adaptation technique for large pre-trained models. The original paper focused on language models. And the idea is that you pre-train and fix a weight layer, and then when you want to update it, fine-tune it for some new application in transfer learning or few-shot learning, then don't update the entire matrix, just update it by a low-rank additive matrix or a low-rank adaptation, okay? You pick some low-rank R, and then you only have to learn D times R parameters as opposed to D times D parameters. And you can see the full model has many parameters and you have to retrain them all if you retrain in full. Whereas for LoRa, you would only have to retrain a small number of parameters and you can get very similar accuracy. Okay, so some of the problems with LoRa is that it tends to overfit on very low few-shot learning tasks. And it's pretty sensitive to that parameter R. You have to pick the rank correctly in order to get the best results. And that's exactly the kind of thing that depth helps with, right? Generalization, not overfitting, and allowing the rank to sort of find itself in the deep factorization. So that's what we propose, is to instead of using just 2 factors here, use a deep factorization. Okay, and we see that, so this is that plot that I showed earlier, just the singular values without the scale. So this is the semantic textual similarity data set. We use a small number of training examples, see here as little as 16, just to fine tune this huge model, right? And the output metric here, Pearson correlation, is increasing both with vanilla LoRa, which means depth 2, right? And also our method, Deep LoRa. The great thing, though, is that as you increase the rank R, Okay, so like when you cross-validate on this method, it chooses rank 8 as the adaptation, right? But if you didn't know that, or you didn't want to do cross-validation and you overshoot, then vanilla LoRa overfits. And the beauty of Deep LoRa is it's, leveraging what we know about deep factorizations and generalization, and it doesn't overfit with this increased rank. And in fact, when you look at the numerical rank of the resulting adapted layers, many of them have not adapted almost at all, okay? Those tend to be the shallow layers that don't need updates because they're just very general, say, language features, right? But then some of them do adapt, say, up to rank 8, which was the parameter for vanilla LoRa. And all the vanilla LoRa matrices used the full rank available. So that's why overfitting happens. Okay, so, and that hopefully explains why there's so few singular values there, because we're not training a full adaptation in that other plot. We're just training this small adaptation, this lower rank adaptation. All right, so in conclusion, we see that gradient descent learning happens in an invariant subspace. We have a specific theory of that for deep linear networks, and the idea has allowed for efficient low-rank training, adaptation, and network compression in both linear and as sub-pieces of nonlinear networks. So thank you for your attention. These are my excellent collaborators, students Suman Kwan and John Yaris. Did a great work. My postdoc Peng Wang, and he's co-advised, all three are co-advised with my colleague Ching Chu. And that's all I have for today. Here are some of our papers, and I'm happy to take more questions.
Okay, thank you, Professor Balzano, for the wonderful talk. Everyone, please smash that clap reaction button. And I guess I will stop the recording and we can take questions.